Hi everyone. Today, our group will present a case study on tunnel construction focusing on the Klang Valley MRT project in Malaysia. This massive urban rail project aims to reduce traffic congestion in Kuala Lumpur by providing a fast and efficient public transport system. The Sungai Buloh Kajang Line, also known as the Kajang Line, spans 47 kilometers with 9.5 kilometers of underground twin-bore tunnels built beneath the city centre. This tunnel uses a circular cross-section and carries single-track rail in each bore. The MMC Gamuda joint venture was appointed as the main contractor using advanced tunnel boring machines, including the variable density tunnel boring machines, a Malaysian innovation designed to tackle challenging ground conditions.
So there are 8 steps for MRT Klang method of construction. So firstly, we will start with site preparation, MRT Klang tunnel. First, engineers studies and they will mark the tunnel alignment. So this means that they will decide exactly where the tunnel will go underground. So there are 2 main shafts. First is the launch shaft and also the retrieval shaft. Launch shaft, where the TBM, which is the tunnel boring machine, will be start digging, and also the retrieval shaft where the TBM will finish and come out. So after that, they will transport the huge TBM parts to the site, and these parts are assembled underground inside the launch shaft and ready to begin tunneling process. So the step 2 is starting the tunnel boring machine. So after the TBM is fully built underground, so it is placed nicely on a tracks and also ready to start digging. So the team will do final checks to make sure that all the parts like the spinning head and also the soil removing system are working properly. And also once everything is prepared well, the TBM is turned on and starts moving forwardly slowly. Front part called cutter head will spin fast to break the soil or rock in front of it. So the soil that gets dug out will be taken out using the conveyor belt or pumped through slurry pipes. Depending on the soil type, this process runs non-stop. So day and night it will be non-stop, and also so they can finish the tunnel safely and faster. Next is installing the precast segment linings. So as the precast segment linings will be the support, and also each time it moves forward, this is what happens. So the cutter head rotates and it breaks the ground ahead, and also the losing soil is sucked out through the conveyor belts or the slurry pipelines. So while the front is cutting, the front part of the TBM is cutting, so the back part of the TBM will install precast concrete segments to form the tunnel wall. Also, these precast segments are like big concrete blocks that fit together in a ring shape. So each time a ring is completed, it will move the permanent tunnel structures. So step number 5 is breakthrough, where the TBM tunnel finally reached the end. So breakthrough refers to the moment where the TBM successfully breaks through the final wall, which is at the end of the journey. So this marks the completion of tunnel excavation process and also is a key milestone in any underground construction project. So this is the very proud moment of everyone involved. And also what happens during the breakthrough. After many cycles of boring and also install the precast segment linings, the TBM finally reached the tunnel endpoint. So the cutter head will pushes through the last soil or concrete barrier, and the machine will becomes visible at the reception shaft.
So I will be explaining about the major issues and challenges faced during the tunnel construction of the MRT Lembah Klang. So let's dive in. One of the main challenges was dealing with mixed ground conditions. The tunnel alignment passed through canny hills, karstic limestone and granite formations. Tunneling through limestone posed significant risks due to the cavities and sinkholes. These cavities often filled with water and made it hard to maintain pressure in the TBM. In fact, sinkholes did occur causing destruction and safety concerns. Emergency stabilization like growth injection was needed to control the situation. Another major issue was the high capital outlay and maintenance costs. TBMs working through hard granite experienced frequent cutting wear, leading to delays and high maintenance expenses. Moreover, the TBM is a complex machine, and if a major malfunction happens, it is not easy to fix because it had to be shipped to Germany for repairs. Next is the challenge of working in a dense urban environment. The tunnel ran beneath busy roads and buildings, increasing the risk of surface settlements and cracks. In some areas, even controlled blasting was used to break rock, raising the public safety concerns. Also, there was limited construction space. Launch shaft and ventilation shaft had to be built in a very tight, crowded areas, causing traffic disruption, especially when using the cut and cover method. Finally, subsurface was created in a serious risk. In certain soil layers, high water pressure destabilized the tunnel face, increasing the chance of collapse. If groundwater control failed, flooding could occur, damaging machineries and causing major project delays. Let me explain how this advanced technology contributes to the sustainable construction. First, the machine helps to reduce the risk of ground settlement and sinkhole. It does this by using a high-density slurry that can precisely be adjusted to maintain stable pressure on the excavation surface. Second, the TBM can minimizing the disturbance of environments. It can switch smoothly between the earth pressure balance and the slurry mode based on the ground condition. Third, the machine ensures the efficient spoil removal through the closed-loop system. The excavated material is crushed and transported hydraulically to a slurry treatment plant, where the slurry is cleaned and reused. Next is reinforced by using the ground treatment method like check grouting and fissure sealings. These techniques stabilize weak grounds and prevent issues like erosions and also the groundwater leakage. Last but not least, the TBM control the excavation method produces lower vibration compared to the conventional tunneling. This reduces noise and structural impacts such as in the sensitive areas, such as urban areas. In conclusion, the MRT Malaysia SPK line stands as a testament to Malaysia's progress visions in urban transportation. By integrating the world-class tunneling technologies and strategic engineering solutions, this project not only overcomes the complex geological conditions but also paves the way for the safer, faster and sustainable public transport. The use of the earth pressure balance and the variable density tunnel boring machines reflects a smart response to the challenging geology of the Klang Valley. Beyond engineering, the MRT SPK line fosters greater connectivity, reduces traffic congestion, and supports environmental by encouraging the public transit over the private vehicle. To conclude this section, this project is more than just an infrastructure development, but it is a model of innovation, adaptability, and long-term impact for the future projects locally and internationally. Thank you.